Well, good evening, everybody. And by good evening, I mean good morning. So glad you could join us this morning. The local time, 8:48, and we'll begin our session this morning at 9 o'clock local time, 12 minutes from now. Go ahead and scrub ahead 12 minutes if you're watching the replay. Otherwise, if you're joining us live this morning, thank you for tuning in. This morning is our session on geologic time. Changed the title once I started thinking seriously about what I wanted to do with you all this morning. So geologic time will start in a few minutes, and then tomorrow, absolute age dating. So these kind of go together. Kind of a 2-lecture combo packet. And I'll talk more about that once we start for real. Good morning. Let's make sure we're all functioning properly here. Audio, visual. Good morning, Denmark. Yes, it'd be wonderful if we had a bunch of folks from the UK. Finland, good morning. British Columbia. Good audio, Neil. Thank you. Nice. Yeah, we're checking the video streaming. We're checking the audio. It's the weekend, and I haven't been out in the backyard for a while, so I'm making sure that we don't have any issues. Japan, good morning. Nice. Glad to hear that. Yeah, you can hear a little pitter-patter, perhaps. Good. Yeah, it's a very quiet morning here. No wind at all. Overcast. And I checked the weather about an hour ago, and it's like, might be a few raindrops. So there were no drops at all until about 3 minutes ago, of course. So we'll see how those, how that functions. I've got an overhang for the laptop. I don't think we're getting wet. I've got an umbrella kind of duct taped to the ladder, so there's maybe about a foot of an overhang of the umbrella over the camera or the iPhone, so I'm feeling okay there. So you might, can you hear the few little drops coming? Pitter patter, yes. So consider that part of the experience this morning. And if you're a regular, you know that we've been in the front porch the last 3 sessions, mostly because of high wind, which is a common experience here in Ellensburg. And old Blackie here got blown over, even though I had it perched right up against this portion of our house. I thought it was a perfectly safe place, but it must have been rocking back against the house, and finally there was a big enough rock that it just fell on its face. So there's a couple plastic guys here. So they cracked. There's kind of some interlocking teeth where you can play with the angle of the board, but I think we're still functional. And, I use wet cloths on the board all the time, so I feel like everything's pretty much able to handle water except for the laptop and the phone, of course, but I think we're okay. New Orleans, good morning from Jason. Boulder, Colorado. I'm just seeing names, whether you're saying you're from Boulder, Colorado or not. James Earl Ballou and Heather, good morning. Terrific to have you all with us. Oh, we're approaching 300 people. Nice. Good morning, Evelyn, age 7. Evelyn, do you live in my town? Evelyn, do you live in Ellensburg? Have we met each other? Something tells me you live in the same town that I do. That's weird. There's a few neighbors that watch. Bill, raining like crazy in Portland. That sounds about right. Okay, well, Evelyn, I'll have to come and visit sometime, Evelyn. We can visit in person. I dropped my globe this morning coming out of the mudroom. I guess the earth is still turning. Okay, special thank you this morning. This is now part of our routine, I guess. FedEx guy showed up again, got a sign for a package. There's more wine from Cedar Mountain Winery. So Linda and Earl from Pleasanton, California sent up another 3 bottles. So it's a little early, but we enjoyed some of this last night and played a little music and had a good old time. But there's still half a bottle here, and the other 2 bottles are much appreciated. So Cedar Mountain Winery, this episode of Nick from Home, brought to you by Cedar Mountain Winery. You gotta love it. Thank you. Visited with Jeff down at Vinman's Bakery yesterday. He's been watching pretty regularly. No pastries this morning. I got one food prop for you this morning. Who else we got here this morning? We're still doing okay on time, right? Yeah, we got 5 minutes. I'm so pleased that we're doing okay with audio and visual. You know, I watch a fair amount now of, as you probably do, a fair amount of live streams and other kind of people recording things from home for various purposes. And with your help, I think we've solved a lot of the issues that some others seem to be having. So I like things to be just right. And it seems like we're pretty close there. Aiden, age 9, good morning. Yes, if we have more kids who are taking a break from Saturday morning cartoons and are joining us against your will, 103 degrees Fahrenheit today. Are you down in Australia or New Zealand or South Africa or something? Or maybe Los Angeles? I guess it's been warm in Southern Cal lately. You hear the jays this morning. I should probably start thinking about what we're going to do here this morning. What's the topic? I love Jolly Ranchers. This episode of Nick from Home brought to you by Jolly Ranchers hard candy. They make your tongue different colors. Aight? Biju's not interested in being outside this morning for some reason. I guess it's the rain. He's not interested in getting wet. It's barely any drops. We don't get rain much here. So it's kind of a treat to be out here with a few sprinkles. It's so calm, I'm about ready to fall asleep. I need to wake myself up, get myself going. I am pleased with these weekend morning sessions. It does seem like we're reaching some extra folks. So I'm going to continue with this schedule. If you're North American people, or South American people, I guess, you just got to get up a little bit. Or Hawaiian, what is it? 7 in the morning there, maybe? 6 in the morning? Good morning, Patrick. Warhawk is pleased with every session. Well, I can sleep better tonight now. Good, thank you. Yeah, we did have a helicopter issue when I started things at 9 o'clock or 10 o'clock instead of 9 o'clock. Okay, I got 2 minutes. I need to start thinking. Thank you. Thanks for joining us. We'll start in a couple minutes. Well, good morning to you all from Ellensburg, Washington, USA. Thank you for joining us this morning. We're going to begin our session on geologic time. And tomorrow morning at 9 o'clock, we will do essentially part 2 of this session about dealing with the great expanse of geologic time and talk more specifically about absolute age dating. So right up front, let me give you a sense that today our objective is to talk about I'll let that kind of play out as we go. But we're saving tomorrow for a very specific discussion. Tomorrow is breaking a rock off of a mountain, bringing it back to a laboratory, and somehow determining the actual age, the absolute age of the rock. And this process cannot be done with all kinds of rocks. There's only certain rocks that you can do the process of actually calculating the precise age, with some error either way, on this age of the rock. So that's what an absolute age date is. And so I'm hoping that you'll be able to hang on to those questions about absolute age dates till tomorrow. So today is talking about other things related to geologic time, And in a way, it's a partially kind of sets you up for tomorrow morning's session. So if you're able to join us again tomorrow morning, I'm hoping that you'll get your money's worth out of that. Okay? So now that I've kind of set that up programmatically, let's get into our discussion of geologic time. Let me start by saying this. I teach at the university. I teach my classes, been doing it a long time. I make video programs for television and the internet and that sort of thing, and that takes part of my time. But there is a third part of my job, and it's speaking to groups across the Pacific Northwest, and I really enjoy that as well. Get invitations from different groups, a big agricultural group, an irrigators conference, Boy Scouts, whatever, Girl Scouts, pretty much a whole rock clubs, all sorts of different groups that want to have somebody come and speak. So that's great. I have learned that at almost every one of those public talks, there's time for Q&A afterwards, and two questions with a bit of an attitude show up. And sometimes it's kind of disguised and not really super obvious which angle they're coming from, but sometimes it's super blunt. Can you guess what those two main questions are? The ones that have a little bit of edge to them, a little bit of, I don't think I'm on the same page as you, buddy, and I want to kind of needle you a little bit on these two topics. Well, obviously one of them involves geologic time. And there's different ways to ask the question in front of, let's say, 200 people that are in this banquet room. But one of them is, how do you know those rocks are that old? And the subtext is, I don't believe the rocks are that old. In fact, I believe everything on planet Earth is less than 6,000 years. And the year is 2020, and there are still, I think it's easy to say, millions and millions of people on planet Earth that firmly believe that the Earth is only a few thousand years. Good morning, Muffler Boy. Wow, nice to see you this morning. Nice to hear you this morning. So, I'm going to try to deal with that a little bit, especially tomorrow, but even today, a fair amount. Other topic, the other question that always comes up, and this is really in the last 10 years, I'd say, climate change. Are you really one of those people who believe that the Earth is getting warmer? Because I don't believe it. It's a hoax, you know. So I've decided next weekend I'm going to try to deal with that. And really, I've been chicken with both of those topics. I've never given a formal public talk, like for YouTube and Downtown Lecture Series, on, you know, determining ages of rocks and the evidence we have for global climate change or global warming, whatever you want to call it. So why not try that here? You know, part of what we do here is kind of experimental, and I haven't tried it before, and obviously the live stream is experimental. So I just decided yesterday, next weekend, I'm going to try to talk about global climate change evidence, and we'll see how it goes. I got to do some homework between now and then. I've got a few ideas of how I want to do it, but that's next weekend. And this weekend is ages of rocks. Okay, without further ado, let's get into it. Let's start with the geologic time scale that has been taught now for a few generations. You take a Geology 101 class or a high school class in earth science, and you are faced with something that looks like this. This is the geologic time scale. Here we are this morning on a Saturday morning in Ellensburg, Washington, USA, 0 million years ago. In other words, right now. And at the bottom of the page is the age of the Earth and the beginning of planet Earth, 4,600 million years, or 4.6 billion years ago. And if you're curious about what happened 4.6 billion years ago, I don't know any more than you do. You probably know more than I do. That's more of an astronomy question than it is a geology question, but we're essentially given planet Earth 4.6 billion years ago. And we are confident we have that much time. Now, I was looking in some of my old Geology 101 textbooks about a half an hour ago, and I was shocked to see this. I shared this with you before. This is my Geology 101 textbook from the spring of 1984. 1984, the University of Wisconsin. The Earth's Dynamic Systems, 3rd edition by W. Kenneth Hamblin. And there's a geologic time scale that I suppose I committed to memory with some mnemonic devices in 1984. But look at the age of the Earth in this geology textbook in 1984. 3,600 million years. And now a more updated version is 4,600. That's a billion years. How did we pick up a billion years of time in the last 35, 40 years? Well, tomorrow we'll talk about developing more and more accurate ways to get absolute ages on rocks. And so these numbers continue to change slightly. I mean, a billion years is a major change, so I was stunned to see that. But with more quote-unquote recent geology, we have more and more precise dates. So if you're like, I took geology 30 years ago and I memorized 65, and now you're saying 66, or I memorized 241 and now you're saying 252, it's getting more and more accurate dates and more accurate samples to tune in a little bit closer. So I think it's fair to say that this will continue to get tweaked as we continue to learn more and more. That's how science works, of course. We don't stay static. We continue to move forward and get closer and closer to very specific things. Okay, well, if you're unfamiliar with this process then, we read our history from the bottom to the top. The Earth begins, the Earth is here now with you and I this morning, and we march our way through these geologic periods or these geologic eras. We don't need to go through all of these, but are you aware of some of the world-famous examples of what happened? Like, why are these dates used as kind of benchmark dates? Why don't we have tons and tons of dates here? We could, but in this most traditional and basic way to present what we have with geologic time, the most famous event is 66 million years ago, when all the dinosaurs go away. Have you thought of this before? First of all, have you realized that dinosaurs don't exist anymore? They're not walking around with us. We can't go to Africa today and watch dinosaurs roam around. That'd be pretty cool, wouldn't it? But we can't do that. They're gone. And they've been gone for 66 million years. And they began. Dinosaurs appeared on planet Earth according to the fossil record, according to science. I'm a science person, right? 252 million years ago. So this Mesozoic era is the age of the dinosaurs, and I don't care what continent you're on, including Antarctica, we can find dinosaur bones, and we can find those dinosaur bones in certain kinds of rocks, and all those rocks are between the ages of 252 and 66 million years ago. There's not one dinosaur bone that's older than 252. There's not one dinosaur bone on planet Earth that's 66. Well, how do you know that? How do you know those rocks are 66? How do you know the dinosaurs? That's tomorrow, getting the absolute ages. But we can do some things today to answer some of these rather basic questions about geologic time. Okay, now imagine you're a 19-year-old kid and you're from Renton, Washington, and you're showing up at Central Washington University, and your first class as a freshman is with me in Geology 101. And on the first 2 days, I lay this on everybody, and you've never thought about geologic time before, 19-year-old from Renton. And then I lay down the fact that humans haven't seen any of this stuff. That according to the fossil record, humans have only been around a few thousand years recording things, and a couple million years in some early form. In Africa, and then eventually going out of Africa and starting to populate other continents less than 1 million years ago. Less than 1 million years ago. North America, for instance, is being populated by human beings. So how can we say anything about the dinosaur time, or even what happened before the dinosaur time? Is this all just story time? How can you possibly say anything if nobody saw it? And as a 19-year-old, many of you are very bothered by the fact that you are insignificant if you look at this whole thing. Steve, I don't mean to be disrespectful now, but your contraption is making a big shadow on my beautiful face. I don't think we need we're not going cozy forward, I don't think at all today. So thank you for your apparatus. It's in the grass temporarily. Okay? So that's a major issue. So, history lesson time. If we talk about geologic time in a Geology 101 classroom, even today, in the year 2020, most of us talk about one person. And if we have any viewers from the UK this morning, especially Scotland, especially Edinburgh, Scotland, James Hutton is an important figure. This is back in the 1780s. Wow, I'm so strong this morning. I had extra rye bread from Vinman's Bakery. I'm just breaking chalk like nothing. So why is Hutton important in Scotland? Well, even the most advanced scientific thinkers in the UK, or anybody thinking about geology in the 1700s, was thinking that the Earth was 6,000 years old. Like, I'm a scientist, and the Earth is 6,000 years old. That was conventional wisdom of the time. And Hutton was a controversial figure because he was out there banging on a bunch of rocks and finding weird things like unconformities, and was doing a lot of deep thinking about the observations he had made. And Hutton was the first guy to say, look, I don't think the Earth is 6,000 years old. I think the Earth has to be millions, maybe tens, maybe hundreds of millions of years old, based on what I'm observing out there. James is basically saying, have you guys been out there and looked? Have you seen these limestones at the top of mountain ranges? Have you seen certain layers that are tilted and other layers that are flat? I don't see how you can do that with natural forces in just a few thousand years. So obviously he was not a popular guy for quite a while in science. He proposed something called Uniformitarianism. Can I write it on the board? Yes. Can I fit it on the board? I don't know. It's a pretty long word. Let's try. Scrabble player? Game over. Triple word score. Uniformitarianism. So the concept is this. Hutton says, I am thinking that humans have been around for, let's say, less than 1 million years, and yet we have this incredible expanse of geologic time before us, before humans ever showed up on planet Earth. And he introduced this concept called uniformitarianism with the root of that word, uniform. So this is the philosophy behind modern science, behind modern geology. Here it goes, in word form. Hutton says uniformitarianism, that's the encapsulation of what I want to try to get across in my scientific papers and the books that I'm writing. Can we assume, says James, that the Earth has all sorts of natural laws, gravity? What happens when a river is flowing towards a cliff? Well, we've been to rivers that are flowing towards a cliff. What happens to the river water when you approach the cliff? It goes over the cliff, and we call it a waterfall. We'll talk about waterfalls in the Ice Age next week. Well, can we assume, says James, that if there was a river going towards a cliff 2 million years ago, can we assume that that river was going to go over the cliff? That gravity was a thing 2 million years ago, even though nobody was there to see the river go over the cliff? Can we assume that when a volcano that's cone-shaped has a whole portion of the mountain slide away, and convert into something like a mud flow? Can we assume that that happened 2 million years ago or 5 million years ago, even though we don't have eyewitness accounts? James basically says, can we please travel the planet? Can we study all these natural processes as carefully as we possibly can? Document these natural laws and how they work, how certain kinds of rocks are created in certain environments. And then can we please assume that even though we weren't around to see it, those rocks were being created in those environments way back when? The natural laws remain uniform through time. And if we assume that and bank on that, then we can go back millions of years and say something with confidence. So let me use my favorite example. Do I have a limestone with me here? Should have grabbed a good-looking limestone. Forgot to do that. Sorry. So limestone is my favorite example of this. We know, as we travel the planet today, that limestone only forms in warm, shallow seas. Limestone, a rock. We've watched it form. We've watched the lime accumulate. It has to be warm marine water. Typically, that limestone has to be warm enough to be within 30 degrees north and 30 degrees south of the equator. So basically, we need equatorial water. Like, think snorkeling. Think your favorite snorkeling spot. Is it within 30 degrees of the equator, latitude-wise? And can you picture what's going on among those corals and those beautiful tropical fishes and all those colors? And then the floor of that snorkeling area is a bunch of little kind of light-colored little broken pieces of coral and other things. That's basically limestone in formation. That's where you create a limestone. Warm, shallow sea, limestone. That's on the planet today. But now what if we find a limestone in the desert? What if we find a limestone in Grand Canyon, which we do? What if we find a limestone in the bottom of Hell's Canyon, which we do? What if we find a limestone in the deserts of central Idaho, where I did my master's thesis? We do. It's a hot degree. It's a hot day. There's rattlesnakes. It's a desert. There's cactus. And yet there's limestone. Can we assume that that limestone in central Idaho, in the hot desert, was formed under a warm, shallow sea? We can, according to the way that we operate with modern science. And so we can go back hundreds of millions of years and say something reasonable about what happened that long ago using the principle of uniformitarianism. Okay, so that unlocks a whole world to us. And therefore, then we have to try to grab our mind or wrap our mind around all this time. Now, you may have seen something like this done. I'm going to do it quickly because I want to get to the relative age dating laws that we're going to use especially tomorrow. Okay? That's my best attempt to give you a little snapshot, a little window into the world of James Hutton and how we transformed from viewing the Earth's history as just a few thousand years ago, which of course was based on the Bible, and you just go back generations of people. You run out of people, you run out of the Earth, basically. The beginning of the Earth, beginning of people, one-to-one correlation. That's why Hutton changed the way we view things. Now, I have to say this. I won't be heavy-handed about it. I'm a Catholic. I pedal my bicycle to St. Andrew's Church every weekend. And I'm a cantor. I'm up there singing. I'm leading the prayers. That's a big part of my life, and especially the music, with all that history, with all those tremendous hymns from hundreds of years ago, are about as spiritual as I get. I'm not a Bible scholar. I don't know the Bible backwards and forwards. But I mention this personal detail to help some of you see that this doesn't have to be a choice. Here's the religious folks on one side of your screen. Here's the scientists on the other part of the screen. Sure, there are plenty of people over here that have no interest in viewing any other thing. And the Earth is 6,000 years, even though it's the year 2020. For sure, let's play some pickup basketball, and in between sessions, let's talk about the age of the Earth. That's happened to me a number of times. Box out the guy a little harder next time. And then there's plenty of folks that I work with who are over here. But there are shades of gray in between. And I'm in the middle somewhere, and maybe you are too. And I see ways, especially with my faith, to make these things work together. That's enough of that. Okay, so do we have any tricks Well, first of all, there are any tricks to memorize these names if we're really going to use these names? As a Geology 101 teacher, I choose not to use these names. They get in the way. But as you get on in geology, in more advanced classes, you need to know these names quite well. So can you come up with a mnemonic device? In 1984, I was taught the mnemonic device, slightly sexist, for the order of the periods within the Paleozoic. I still use it today. I'll use it right now without even looking. In fact, these words are backwards. Order of the periods in the Paleozoic. Campbell's onion soup develops Miss Pennsylvania perfectly. Campbell's onion soup develops Miss Pennsylvania perfectly. Okay? So there's all sorts of little tricks, but that gets away from the excitement to me. We use these words because it's just shorthand. Instead of saying there used to be a warm, shallow sea at Cincinnati, Ohio, 444 million years ago, which is true. Instead of saying all that, we can just say during the Ordovician, there was a warm, shallow sea at Cincinnati, Ohio. You just save words. Okay, but the thing that I think you've heard of is ways to take all this incredible time and make it equivalent to something that we can comprehend. I'm pointing to my head a lot. I don't know why I'm doing that this morning. Okay? So this is, federal deficit time now, and talking about billions and trillions, and it's like, what? I can't picture any of that. Well, I think I want to move on. It's already 9:23. So my favorite way to take all this time and make it equivalent to something we can relate to is one calendar year. Go from January 1st to the next January 1st. We've all experienced a year. In fact, some of us have experienced more years than others. But we know what it's like to go through one calendar year, right? So if we crunch the numbers on this and take 4.6 billion years worth of time and make it equivalent to 365 days, you know what I'm doing now, right? This is January 1st. We just had our New Year's Eve party. We're starting out the new year with all sorts of optimism for 2020. Good Lord, what were we thinking? By the time we get to the end of the Precambrian, in other words, 541 million years ago, that's Halloween. The Precambrian, this time when we actually had essentially zero life on the planet according to the fossil record. During the Precambrian, there are no animals walking around on continents. There's no birds. There's no people. The only life we have that we've been able to find in the fossil record from the Precambrian, which is 10 of the 12 frickin' months of our year, more than 3/4 of our year, it was a spooky place here on planet Earth. The only life were these microscopic animals that were living in the oceans. No fishes, no whales. I mean, if you took a college class in the Precambrian, play along with me, you wouldn't have had to take biology. There was nothing to study. The continents were full of wind and rock, but not even grasses. Okay, you get the idea. And then something happened, quite mysterious to most of us even today. Something happened where we have something called the Cambrian Explosion. And suddenly the fossil record, slightly younger than 541 million years ago, means we've got all sorts of life suddenly on continents. Not all the life that we know today, but early life is beginning. Little trilobites and other little beetle type things crawling around. And we have suddenly plenty of fossils to look at in the Cambrian period of the Paleozoic, but I'm getting distracted now. So Halloween is here. Oh, the beginning of the dinosaur time? Oh, listen up, kids. Oh, dinosaurs, back at the dawn of time. Oh, boy, can you go? 10 shopping days left. The dinosaurs begin on December 15th. The dinosaurs become extinct 66 million years ago. That's the day after Christmas. And the Ice Age, which will be the topic of all of next week, the Ice Age floods. The Ice Age begins 2.6 million years ago. That's way up here, 2.6 million right there, beginning of the Quaternary. Where is 2.6 million on our calendar? Can you guess? The beginning of the Ice Age. You're half in the bag. You're at your New Year's Eve party, you're hosting, and somebody says, oh, we got to get people together. We got 1 minute. We got 1 minute before the ball drops. Dick Clark's Rockin' Eve, we got 1 minute left. That's the beginning of the Ice Age, 1 minute before midnight. Hey, get over here. In all of recorded human history, the Greeks, the Romans, blah, 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 all this stuff, all this history, all this recorded history in the last 5 seconds of our calendar year. 5, 4, 3, 2, 1, Happy New Year. So as a 19-year-old from Renton, that shakes you up a bit. But that's the whole point. Geologic time, almost everything happened before we show up. I mean, we're pushing these dates back further and further, but we're assuming that in North America, we don't have people in North America until 20,000 years ago-ish. 20,000 years ago. I'm talking about Native Americans not even here until 20,000 years ago. Wow. Really changes the way you view things. Okay, so that's kind of the heavy, head-touching part of this morning. It's already 9:30. The other thing I want to do, and then I'll be very curious about what you want to ask about, especially if you're a child and hearing some of this for the first time, but if you're a person of all ages, what might you want to expand on here, knowing that we're not going to talk about the absolute age date thing until tomorrow, right? All right, let's burn through some relative age dating laws to help us realize that we can, if we look at a canyon wall, we can put things in chronologic order. In other words, each rock layer is representing a different thing that happened long before people, but we can use some logic and study the geometry of those canyon walls and those rock layers and say, well, that had to have happened first. I don't know when, but that had to have happened first, and then that, and then that. That's what relative age dating is, and that was the original title of this session until people started joking about marrying your cousin and stuff. And I've heard it all before. But anyway, I thought I'd come up with a different title because I thought I wanted to talk about uniformitarianism a little bit. Okay, so relative age dating. So I'm barely using the whiteboards this morning. I'm about to use the chalkboard a fair amount, but this is our remaining task with our session before we open it up to you. There are 3 basic laws that we use over and over and over again in modern geology to help us put things in relative order. That's what relative age dating is. The only goal of this is to put things in order. Chronologic order. Okay, so let's do it. So what was the first one? Are you taking notes? Superposition. And to do that, let's go to the Grand Canyon. What state? Northern Arizona. We can go anywhere in the world, you know, to do this, but I'm a North American person and Pacific Northwest, but let's leave the Pacific Northwest and go to a very famous place where we have the walls of the Grand Canyon look like that, don't they? This is one of my older Geology 101 textbooks by Stan Chernikoff, University of Washington, that I've showed with you a fair amount of time. And here's his artistic friend. I can't remember his name. And these are, you know, famous layers. By the way, I had a friend of mine who said, have you ever rafted the bottom of the Grand Canyon? I'm like, no, I never have. I've hiked down to the bottom from the rim a few times, but I've never rafted that. He says, well, I think we need to do that. So he got a group together, got the boat reserved, all this kind of stuff. So about 25 of us were set to raft the Grand Canyon this September. I guess it's still possible, but with each passing day, it seems less likely. So the plan was for Liz and I to join all these folks, and we would spend 7 days or 8 days going down through the bottom of the Grand Canyon. Hope that still happens, but I've never done it. Maybe you have. So the first rule that we're talking about is the law of superposition. This is kindergarten now. This is very easy. The law of superposition says if you have a bunch of flat rock layers stacked one on top of another, this one has to be older than this one. The oldest layer's at the bottom, the youngest one's at the top. That's it. But it makes sense if you think about it. And you're like, hold on. I don't think you can assume that. Let's say you want to argue the rule of superposition. I don't know. If this happened 100 million years ago, how can you say that? Well, my answer would be, let's think about it logically. Are you really guy who's arguing now? It's fine to argue. It's fine to be skeptical. Science is built on skepticism. That's healthy. But at some point, you might have to back away if you use enough logic. How can you argue the other way? If this happened 100 million years ago, are you really arguing the opposite? That this is the oldest layer, and then we made a layer after that below it? And you're like, well, couldn't you make all the layers and then turn them all upside down? Yeah, you can. That's happened. But originally, the rule says we got a bunch of flat rock layers, and the one at the bottom is the oldest. The analogy I use that seems to work with my students, okay, we're going to go to some famous person's childhood home. It's like a living museum, and there's their bedroom. I don't know, Abe Lincoln? Sure. Abe Lincoln's childhood home in Springfield, Illinois, I guess. And there's this bed that was made in 1848 and hasn't been made since. Just play along with me. Now, did we see Abe Lincoln make his bed in 1848? No. But we can assume we know how he made his bed. It's just like how we make our bed, right? He laid down the sheet first, and then the blanket on top, and then some decorative quilt that his grandmother made for him. In other words, he didn't put the decorative quilt down on the bed and then then took the blanket and got in his teeth and slid the blanket under the grandma quilt. And then, oh yeah, I need a sheet too. Oh, I'm getting one of those sheets. That's flimsy. Now I got two things I gotta lift up. I'm gonna be spread eagle on Abe Lincoln, spread eagle on my bed, and I'm gonna lift the sheet underneath. I'm thoroughly wide awake now, by the way. Come on. Superposition. Oldest is at the bottom, youngest at the top. And you're like, well, how old is old? That's tomorrow. But we can use relative age dating to say this one was made first, second, third, fourth, fifth, like chapters in a book. Chapter 1 happens, and then chapter 2 happens, and chapter 3 happens. You're like, well, why would you even bother doing that? Why would you even use the principle of superposition for the walls of the Grand Canyon? Well, you know the answer, don't you? You can tell a story, a pretty fascinating story about northern Arizona. Once upon a time, there was a beach. And then the beach left, and this whole area was flooded with warm, shallow seawater. I guess number 2 is a limestone. And then the sea went away. And there was a desert here, cross-bedded sandstone. And then there was a volcanic event, and a basalt lava flooded onto the scene. And then the volcanic eruption was done, and another warm, shallow sea came. Using relative age dating, using law of superposition, you're telling a story with different chapters as you go from bottom to top. And that's the most basic and fundamental way to approach a canyon wall like that. Thank you for playing along. Next one. And it's prop time. The law of original horizontality. Okay? The law of original horizontality, just like it sounds. Of course, there's tiny exceptions to all of these, but we're doing most basic approaches to most basic places on planet Earth. Number 2 says, you got a bunch of rock layers? I'll bet you they were flat when they were made. I'll bet you they were originally horizontal. Like that. They're still horizontal. It turns out these layers are hundreds of millions of years old. If you're with us for the Hell's Canyon session, when was that? Last time? Was that Thursday night? Yeah, I think it was. Our most recent live stream, number whatever, was on Hell's Canyon, and we learned that Hell's Canyon has 200 million year old limestone at the bottom of it. And we learned in the Hell's Canyon session that Kaibab limestone in the Grand Canyon is 270 million years old. The point is, we do know the ages from absolute stuff tomorrow to know that these are incredibly old layers. And in the Grand Canyon and Hell's Canyon, to be honest, the layers are just as flat as the day they were made. So why is this even a rule? This seems like even dumber than number 1. Well, there are mountains. And quite often, mountains don't have flat layers. But those non-flat rock layers in your favorite mountain range, if we go back in time, the mountain range isn't there. And the rock layers are flat. Now that's powerful and can be used regularly if you're a mountain person. Where can we go? Well, we could go to almost every mountain range on planet Earth. But let's go to my homeland. All my people, all my Zentner people go back to one little tiny village in Switzerland. It's called Elm, E-L-M, like the tree. You can maybe find it if you're curious. Half the little town has still got a bunch of Zentners in it. Zentners all over the gravestones. My great-great-grandfather, Nicholas Zentner, came over from Elm, Switzerland in 1864. And you look at the mountain layers above Elm, Switzerland, or any beautiful mountainous scene in the Alps, or the Himalayas, or whatever, and probably should have gone to the Cozy Fort. I've got a bunch of beautiful photos of mountains with layers that look like this. Looks like looks like Aqua Fresh toothpaste, if you're familiar with that brand. This episode of Nick From Home brought to you by Aqua Fresh toothpaste. So I think if you're a tourist and you have a camera, that's most of us, and you get off the tour bus, that's some of us. That doesn't sound like a good way to travel for me, but whatever. You get out there in the parking lot and you got the little Swiss bells, you know, and the cows and the cheese and the chocolate and everything. And you see this mountain face. Oh, honey, get a photo of that. And all of us, including geologists, will take a picture. That's amazing. It's a mountain with these beautiful, swirly rock layers. But in addition to the beauty and the uniqueness of those swirls, as geologists, we're thinking a little bit extra. Or maybe even muttering to ourselves as we're screwing around with our camera. My God, how did those layers get like that? Because they used to be flat. Those rock layers above Elm, Switzerland were not made like that. They were originally flat, like the Grand Canyon, and something happened to convert the flat layers to something like this. So you need certain temperature and pressure conditions, and of course you need enough geologic time, and you need enough geologic force to do that. I'm reaching into my pants now. And for about an hour and a half, I've had this big hunk candy bar on my belly, tucked into my shirt, shall we say. And I've had that. Muffler Boy is now parked and wanting to listen to this portion of the lecture. Must be live streaming in his truck. Now he's idling outside. I promise, just like last time, I'm not going to talk about that. So in other words, I have a warm Big Hunk candy bar. It's been heating up on my belly for an hour and a half. And because it's warm, and these rock layers are originally flat, if it's warm, we can have these layers fold. Originally flat, but we can squeeze, and we can keep squeezing, and we can keep squeezing, and we can keep squeezing. And you can get amazing geometries if the temperature and pressure of the rocks are appropriate, and if the compressional vice, the tectonic vice in the Alps or the Himalayas or the Appalachians or many of those continent versus continent collisions we were talking about whenever that was. Okay? Now does the law of original horizontality make a little bit more of a mark with you? That you look at this, you know something bizarre must have happened, but mentally, as geologists, we're originally visualizing the flat and horizontal Big Hunk candy bar. Okay, I got one more for you, and then we're coming to you. It was peaceful here until recently. Cross-cutting relations. This is the most helpful and useful law to put things in chronologic order. I'm even going to give you a little test here in just a second. Let me explain the story first of all. First way to say this, I'll do it verbally. Cross-cutting relations. You ready? If a geologic feature cuts across another geologic feature, it's got to be younger. If a geologic feature cuts across or interrupts another geologic feature, the one that's doing the interrupting has to be younger. We didn't see it, but we can use logic. Oh, I'm not even going to draw it. Oh no, I got an idea. So here's part of the cardboard box where the wine arrived yesterday. Thank you. What should I draw here? You suggest. What should I draw? Anything. I'm going to wait. There's a delay on the comments, but this is viewer request time. A cat. Okay. Can I draw a cat? I'll try. I'll try to draw Bijou. There's Bijou. Bijou's laying down. Goodbye, Muffler Boy. I will miss you. JK, not really. Is he gone? Yes. Jesus. Okay, Bijou is... Bijou is sleeping right now in our bay window, dreaming about certain things. Okay, so I just drew Bijou. That's the first thing to happen. I would never do this in real life. Right between the eyes. Trademark. I'm going to interrupt Bijou. Right between the eyes. You got to love it. I'll make up with him after this. So I've got Bijou. Bijou is here first. Bijou is sleeping. Z. I guess that means snoring or something. I don't know. And then I decided to cut Bijou in half and offset Bijou by a normal fault, or offshoot Bijou by a reverse fault. But the point is, I made Bijou first, and then I interrupted Bijou right between the eyes. Now, this is a fault that is cross-cutting the cat. Can you argue the other way? Seriously, can you argue the other way? Can you argue that the fault was there first and then the cat came later? And half the cat, you know what I'm doing. So, the cross-cutting relation rule, which is used for faults, good morning. So you're using, first of all, you're using superposition, aren't you? That here's 4 rock layers in the wall of the Grand Canyon, and they're flat, and they're stacked one on top of another, so this has to be the oldest and this has to be the youngest, just out of those 4 rock layers. That was rule number 1. And now we're doing rule number 3, which is the rule of cross-cutting relations that says if something cuts across something else, it's got to be younger. So this is a geologic fault right between the eyes. And it is interrupting our 4 rock layers, correct? So our rule says if something cuts across something else, it's got to be younger. So doesn't the fault have to be number 5, chapter 5 in our story? Again, you can't argue, can you, that the fault was there first, like during chapter 0, and then these rock layers were like, come on. So you can do it with faults that interrupt something else. You can also do it with granite, a blob of liquid magma. Again, chapters in a book. Chapter 1, chapter 2, chapter 3, and then here comes this liquid blob eating up from below, interrupting layers 1, 2, and 3, so therefore we know that the granite came after the 3 rock layers. This is grade school. This is quite simple, but we use it all the time. And a little sneak peek to tomorrow morning, when we actually come up with the process. Tomorrow morning is absolute age dating. Oh yeah? That granite came up after those 3 rock layers were made? When? Did that granite solidify into rock 1,000 years ago? 1,000,000 years ago? 1,000,000,000 years ago? How can you possibly know the answer? That's tomorrow. We do something by breaking these granites open and analyzing the elements inside of the minerals. Okay? But even though we don't know if this all happened 1,000 or 1,000,000 or 1,000,000,000 years ago, we can still put things in order. That's what we're doing right now with relative age dating. So this is a test for you right now. I'm going into my little course pack that costs less than $10, not available for sale. A bunch of you want a copy of this. I'm sorry. I'm sorry. I'm sorry. I know it's 9:51, but we're almost done. Here is a made-up canyon wall. Can you see it all in your frame? Yeah, I can even come in closer, right? And can you put these letters in order, please? Actually, you know what? I'm going to wait. If you're feeling like you want to just put yourself out there, and there's a risk of getting embarrassed now, but can you type out the proper letter order? Like, does it go L, C, N, A, R, C, whatever? I'm going to wait. If somebody wants to give it a crack, I promise I won't embarrass you. I want the full order, not just the oldest or not just the youngest. Thank you, Richard, for giving it a try. You know, this is kind of, I'll stall for you here a little bit. But if you're training to be a teacher, I've always felt it's a little bit overlooked about how you build a certain vibe in a classroom. And those of you that are good teachers already know this, but you develop a certain amount of trust with your students. And the main message is, and you can even verbally say it in the first part of the class, you can't get embarrassed here. I'm not just going to casually say, any questions? Because nobody says anything. But if you actively build in these questions and you make sure that you know that everybody in the room is valued and you're not going to shame somebody, even though privately you might want to go, that was a really stupid thing to say. You never say it. You're always encouraging. And by the end of the quarter, you have everybody participating. The bright folks, the dull folks, everybody's participating, and they feel like they're not going to get bamboozled or wamboozled or some other word like that. So I see many of you are chiming in now, and I'm going to give you the answer. I'm not even going to take the time to scroll through, but thank you for playing the game. What are we doing? We're finishing up by using our relative age dating laws, superposition, original horizontality, although not really, and mostly cross-cutting relations. We're using cross-cutting relations over and over and over again. And I'm looking at this backwards, but I think I've used it enough that I'm not going to make a mistake by looking at it backwards. Here we go. The oldest layer is X. It goes X, A, Q. So let's stop right there. How do we know Q is not the oldest? Q is down here at the bottom. Superposition says layers at the bottom are the oldest. But can you see, first of all, that the pattern and the shape of Q is blobby? Like this. So just by looking at the geometry of Q, we can infer, can't we, that this is not a sedimentary layer, but instead it's liquid? Q was liquid, just based on its shape. And more importantly, Q is interrupting X and A. So in other words, X was a flat layer and A was a flat layer using superposition. And then Q came in and ate through or interrupted X and A. You know, it's like having a conversation in the science building. We split our new building with physics. And all the physics people are very wonderful. But some of them are a little rusty on social skills. So of course, I'm the hero in every story that I tell. So I'm having this conversation with a fellow geologist, and we've been standing there for 5 minutes talking about whatever. Talk, talk, talk. Now here comes this physics professor down the hall. And a sane person would wait until we're done talking, or at least get a cue. But the physics person just comes in and just starts talking to one of us like the other person doesn't even. They interrupt our conversation. The conversation got established already. Physics dude coming in. I mean, come on now. So, I was talking, the other guy was talking, then physics dude comes in, interrupts both of us. But Q has to be older than R. Why? Well, I'm showing that there's this strange pattern around the edge of this liquid Q, but there is no squirrely pattern up here, but there probably was. There was probably more A there originally. And so because the fact that Q is kind of beveled off and lost its top, we know that R had to come in after Q. This is a brief diversion, but there's something called an unconformity, which was the focal point of Hutton, to bring it back to James Hutton. one of the key places that is now a World Heritage Site, I believe. Sicker Point, is that how you pronounce it? Sicker Point is in Scotland. And Hutton just sat at this place. Is this on the east coast of Scotland, I think? And he's like, why are these layers like tilted at such a steep angle and these guys at such a lower angle? And he realized you just can't explain that unless you have incredible amounts of time to, I'm not flipping you off, thought the ladder was falling. I guess it's not. So this is the concept that Hutton was able to put together and realize that at that red line, there has to be millions of years because we're tilting the layers below and we're not tilting the layers above. Let's finish it out in case you're on the line now. You don't want to be thoroughly embarrassed, so let's give you the answers here. And by the way, I'm not clever enough to make these letters spell something. Like, Muffler Boy or something. I'll actually write it out for you. Thanks for your patience. If you've had this question that you've been sitting on for 45 minutes, I realize I'm running late tonight, this morning. All right, so I'm just going to write this out. X, A, Q, R. And now we got L that's cut by both faults. And then N, and then C, and then B, and then Z. That's the answer. And if you had that, way to go. And if you didn't, it's okay. Thank you for playing. The reason that we know that fault B, which is a crack, interrupts, that B has to be younger than N because B is interrupting N, like N used to be just a straight crack, but it's clearly been offset. And Z has to be the youngest of everybody because it's not broken by anybody, including fault B. Okay? And if I made a mistake, then that's really tragic, but oh well. Thank you for your patience. 10 o'clock, that's almost a record, probably is a record. I think the columnar basalt thing went long as well last week, but that was for other reasons. It's time for live Q&A. I'll stick with you for 10, 15 minutes if you feel like you want to join us that long. If you've had enough this morning, thank you for joining us. But let's go ahead to your questions. It's starting to sprinkle again, so I might... I love my laptop so much. I might get this over it somehow. I don't think a few drops is going to hurt it. Oh, don't you have Apple warranty, whatever? No. Okay, scrolling back, looking for uppercase questions. If all the rock is sourced from the same magma, how can rock have different dating? P. Clement. I'm not inferring that all rock is from the same magma. This is more tomorrow, but let me try to address your question. We have sedimentary rock layers like a sandstone, and every grain of sand in the sandstone is broken off pieces of rocks that are from other kinds of rocks. And you'll see tomorrow that we can get an age for when those sand grains were brought in by finding a layer that we can absolute age date above and below and sandwich the particular age that those sand grains came in. So we can't do absolute age dating on sand grains or sandstones, but we can with different magmas. But your assumption that all rocks are sourced from the same magma, I don't see how that works. And we can follow up on that tomorrow. How do geologists decide when the Holocene ends and the Anthropocene starts? Jackie, the Anthropocene is a new term. So in other words, each of these periods can be split into smaller subdivisions yet called epochs. So you may have heard the term Pleistocene. The Pleistocene epoch is from 2.6 million years ago to about 10,000 years ago. And then the Holocene is the last 10,000 years of time. And there's a new term that's been introduced. I don't use it, but it's talking about this dramatic change in global climate records and global climate evidence, and Anthropocene suggesting that we have a new collection of geology to categorize. So I don't have an answer for you, and I don't know how those that are using Anthropocene are using the starting date for that. So that's kind of in progress as I see it. How do you pronounce Oligocene? I think I just did. Again, you know my deal, right? I'm not big into words that get in the way. And to me, you know, if you're talking about your geologists have coffee or beer or something, oh, well, in the early Miocene, such and such, and then this and the Paleocene, boundary. It's just jargon that feels like a secret language for a secret club. That's not my approach. And that's why I typically don't use terms unless they are helpful to us. That's my call on when it's helpful to us or when it's not. Hang on now, hang on. Getting a lot of rain on my computer now. I'm starting to... Maybe this will work. Cozy Fort. Why do American geologists divide the Carboniferous period into Mississippian and Pennsylvanian? Sam, thanks for the question. Are you from the UK? Yes, Carboniferous is a period that was used, I think, originally over in Britain, and there were some specific coal beds in the Appalachians that Americans decided to split that carbon-rich time into two units. I don't know much more than that. So you're right, Mississippian and Pennsylvanian is an American subdivision. Would one exception to the cross-cutting rule be a river? The cross-cutting rule is only working with rock layers. And you're right, if a river is carving, well, yes, in the case of remember our discussion of rivers being there before the ridges started to lift up? That would be an exception, that's right. So there are plenty of, by the way, in general, I love giving up with basic rules and organizations, but there's so many exceptions that, you know, if you got the wrong vibe in the room, somebody's got their hand up. Well, actually, you know, all volcanoes have been found at plate boundary. Well, actually, Hawaii is not a plate, you know, it's like, okay. So you're right that in some cases, rivers don't follow this rule, but I would think of the cross-cutting relations rule most helpfully with our canyon walls or other rock layer situations. What's the deal with the rocks underlying Alki Beach South? Well, we're kind of off topic here, Jason, but that's the Seattle Fault that we discussed a while back, and the south part of the Seattle Fault lifted 21 feet compared to the north side. Thanks for the question, but I think we'll try to stick with I don't see how that relates to what we were talking about. And if it does, I don't see it. I'm sorry. How might layer C from the example be two different thicknesses? Happy Disco Jesus. Thank you, Happy Disco Jesus. Oh, I got to go get that thing. Hang on. just stepped on my big hunk and shattered it. Oh, so Happy Jesus, or whatever your name was, Happy Disco Jesus, is noticing something interesting, that I have rock layer C of 2 different thicknesses. And he's like, how's that possible? Or she, I don't know. Well, one side of the fault, this is actually, for those advanced students, what kind of fault is fault B, as in boy? Is it a normal fault or reverse fault? I'm not going to go back and do that all. It's a normal fault. And how about fault N? I didn't even know I was doing that, or maybe I did. Yeah. I guess I was trying to trick my students. Fault N is a reverse fault. That's a dirty trick. And fault B, as in boy, is a normal fault. And if you don't know how to do that, maybe you can find our whatever live stream talking about faults. I guess it was the Seattle Fault episode. Anyway, to answer your question, Happy Disco Jesus, you can think of this side of the fault B as lifting up. And when you lift, you intensify erosion. Or if you do the opposite thinking, and the right side of fault B drop down, and so you preserve. So layer C was uniform in thickness across the way, but it got shaved away on the left side of the fault because it was the uplifted side. And I was trying to show that with that fault sketch. Thank you for the question. In a river valley fault line, is it possible to have uplift on both sides of the fault? In a river valley fault line, is it possible to uplift on both sides? I don't see how you can uplift on both sides of the fault. Well, you know what I can do? Hang on. Oh no, then I would get my camera wet. I'm not following moto mining. I don't see how you can get uplifting on both sides, uplift on both sides of a fault. I've never seen that. I thought it was called an epoch, not an epic. E-P-O-C-H, epoch. That's how I pronounce it. But I'm from Wisconsin. If layers are cut over time, they can be folded as well. Show both, cut and fold in one formation. Richard, that's not a question. Do you agree the overflow theory at the Grand Canyon is debunked? Barry is asking about the Grand Canyon overflow theory. I'm guessing what you're asking, Barry, is, well, I don't even really know much about the overflow theory of cutting the Grand Canyon, but I assume that's a catastrophic flooding and carving the Grand Canyon in just a few thousand years. And if that truly is the theory, then there's all sorts of geology. Can't go into it right now, but there's all sorts of ways to get absolute age dates on the deposits of things that were carried out of the Grand Canyon that prove that it formed over millions of years of time. So yes, if I'm following your thought there. If a plate pushes up a mountain range near an ocean, this is from Evelyn, age 7. If a plate pushes up a mountain range near an ocean, does that make it harder to determine the age using the rules? Mountain ranges do get pushed up near oceans. I don't think that would make it harder though, Evelyn. Our rules of helping us get an age for folding and faulting work in most of those settings. Thank you for the question. Did you ever find out who the uncredited artist was in Chernikov's book? I still use it. I'll look it up. Is the oldest age based on solidification, prior time when molten? Well, we'll see tomorrow that we can only get absolute age dates on certain kinds of rocks, and many of those are rocks that cool from magma in a relatively short amount of time. In the case of our example, the layers at the bottom were sedimentary layers, which can go back much earlier in time. What are the large, chalky, diatomaceous lake layers between Missoula flood layers? What are the large, chalky, diatomaceous-like layers between the Missoula flood layers? Catherine, can I save that one till next week? We're going to have an episode on Wednesday talking about slackwater sediment layers in the Ice Age floods. It's volcanic ash, by the way. Couple more and I think we'll quit. I skipped down to pretty recent now. What was Bretz's great flood theory made fun of because it went so far against the rules of dating? Thanks for the question, Jason. No, Bretz wasn't using any absolute age dates. He was using a little bit of relative age dating where he had a divide, for instance, that got blasted away by a younger flood. But his idea, Bretz's idea of catastrophic ice age flooding was mostly challenged because he needed so much water to happen in a short amount of time. And this is back in a time when Hutton's Uniformitarianism was interpreted as everything happens very slowly and very gradually. And so if you're a geologist, this is 100 years ago now, if you're a geologist talking about a catastrophic flood, that's not the way to go about things, say conventional scientists. Like you must be some sort of religious person. You must be talking about some sort of Noah's flood without them looking at the evidence. So again, it's not black and white. There's always shades of gray. You have to do the work, read the reports, not just jump to your kind of preconceived conclusions. How about two more before we get too wet here? Any chance of doing a show about Alberta's geology? I'd love to, Rodney, but I don't know anything about Alberta's geology. I barely know things about Washington geology. Sorry. Missing billions of years and unconformity with erosion be explained. Let's finish with that. So this will be a nice way to finish, because we're going to circle back to Hutton one last time. So there are these things called unconformities, and they are very important. Let me draw a classic unconformity for you. So we're in a canyon. Could be the Grand Canyon, could be any favorite canyon that you have. And let's say the bottom half of the canyon wall has a bunch of rock layers that are tilted like this. And then the upper half of the canyon wall have untilted layers. And I would guess most people that see that would just go, oh, that's kind of cool, and not think much of it. But Hutton was the first guy to really ponder this geometry. And remember our number 2 rule. Rock layers are originally flat. It's very difficult to convince most geologists that rock layers are made at a tilt like that. They're made flat. So basically, Hutton is saying to himself, well, if we go with my basic assumptions for modern geology and thinking about the past, and we know that layers 1, 2, 3, 4, and 5, if we know those layers were originally horizontal, can we do that mentally? First of all, can we get these 5 layers like flat? And then Hutton's like, okay, layers 1 through 5 are flat, but now we have to start tipping those layers. And as we tip, I don't know, think like sheets of plywood or something. Can you think of like, I used to watch Batman on television as a kid. And at the end of every 30-minute episode, Batman and Robin were in trouble. How are they going to get out of that predicament? I'm not a big comic book guy, but I remember that. And I may have made this part up, but like in one of the episodes there was like a ceiling fan but it wasn't just a ceiling fan, it was like a circular saw. Does this exist? I don't know, maybe somebody can find it on YouTube. And Batman and Robin are in this room, and the floor keeps getting higher and higher in this room, and Batman and Robin are getting closer and closer to this ceiling fan. And how are they gonna, avoid getting, That's kind of what we want to visualize here. Layers 1 through 5 are being tilted, and we're actually lifting layers 1 through 5. And if we uplift, that's what we're doing, we're going to uplift these sheets of plywood up into the ceiling fan. And the ceiling fan is going to bevel those uplifted corners of the sheets of plywood. That's going to take a long time. And so by the time we're done with the tilting and we get them to this 60-degree angle or whatever it is, and we go back to the business of making rock layers, a bunch of chapters have gone by. Chapters 6 through 9, we weren't making rocks, we were eroding the heads of Batman and Robin, and blood is splattering all over the walls. Sorry. So there was time going by on our stopwatch, but we weren't making layers, we were chewing away portions of the layers. And then, by the time we go back to making rock layers, we've already lost a few chapters. That's why when you put your finger on this line, it's not just a line. It's a gap in the rock record representing missing time. In fact, in geology, we have a special symbol Chapter 6 through 9 is representing the unconformity, or the unconformity. That finger you can put on that unconformity represents tens of millions of years. And that's why the unconformities are just as important as the rock layers themselves. Even a line can tell a story. Not just the rock layers, but a simple boundary between two rock layers. Unconformities. And Hutton was the first to think about that and think it all the way through, and we now fully embrace those ideas. A toast for you. Thank you for joining us today. Here's to bee-headed cats. Here's to shrapnel of Big Hunk Candy Bar. And here's to you as you continue to spend time with us here in the backyard, trying to stay busy, trying to stay healthy, trying to stay connected with people that we feel a connection to. And if nothing more, hopefully that's what these sessions are doing for you, in addition to learning a few new ideas about geology. Here's to you. This is the week that was. This was what just happened. And you are certainly welcome to come tomorrow. We'll probably have people of different backgrounds and different levels of openness to embracing what we will talk about tomorrow, but I'll do my best. So tomorrow morning at 9 o'clock might be one to remember. Thanks for joining us this morning. We'll see you tomorrow morning from Ellensburg, Washington, USA. Goodbye. I love you.